Welcome, everyone. So we've spent a good amount of time building up our foundation in mathematical theory. Today is where it all starts to pay off. We're going to see how these abstract concepts, functions, variables, equations, are not just for the classroom. In fact, they become one of the most powerful, concrete tools a business leader can possibly have. We're going to transform complex, messy business challenges into clear, solvable problems. All right, here's our game plan for today. First, we're going to frame why this is so much more than just numbers. Then we'll build up from a single linear equation to something much more realistic, a system of equations. From there, we'll see how to visualize these systems, which is a game changer. And finally, we're going to tie it all together and apply everything to a real-world decision that you will almost certainly face in your career as a manager. Okay, let's dive right into our first section. Look, I know that for many of you, a course like business math can feel like, well, a prerequisite, something you just have to get through. But my goal today is to completely reframe that for you. I want you to start seeing mathematics not as a hurdle, but as your first, and maybe most important, tool for real strategic thinking. This is what gives you a competitive edge. To get us into that mindset, let's start with a big question. Think about a CEO. They have to make huge decisions, right? Should we launch a new product line? Should we build a new factory in another country? Should we acquire a competitor? What are they really doing when they make that call? Well, they're weighing dozens of variables, costs, potential revenue, market demand, labor supply. They're working within very real constraints, their budget, their production capacity. And they are trying to optimize for a specific outcome, usually maximizing profit or market share or long-term growth. At its absolute core, that entire strategic process, it's a massive, incredibly sophisticated math problem. So let's move on and see how this actually works. You know, back in introductory algebra, we get really comfortable with x and y. It's a nice, simple, two-dimensional world. But the real business world? It's not that simple. It's messy and complex. So we need to see how those basic linear equations that you already know can evolve to actually model that complexity. So let's start with a quick refresher on the formal definition. The two key phrases here are straight line and constant rate. Now, constant rate is important. It means we're modeling relationships that are predictable. For example, if it always takes 2 hours of labor and $10 of material to make one widget, that relationship is linear. It doesn't suddenly take 5 hours for the 100th widget. But the most important part of this definition for us in this course is the idea of variables. In a business, what are those variables? What are the X's and Y's that a manager actually worries about? And boom, this slide right here takes us immediately out of that simple two-variable world. A real business doesn't just have an X and a Y. It has production costs and labor costs and shipping costs and marketing spend, dozens, maybe hundreds of variables all interacting at the same time. This equation with X, Y, and Z is a much more realistic, though believe me, still very simplified, model of what a business actually looks like. And this is the magic trick. This is the translation from abstract math into concrete managerial action. These are not just letters on a page anymore. Suddenly, X becomes the number of units of your main product that you're making every single day. Y becomes the total number of employee hours you have to work with. And Z might represent the cost of raw materials per unit, which, as you know, can fluctuate. An abstract equation has just become a dynamic model of your entire operation. So if we accept that our business is this complex web of interconnected variables, production, labor, costs, and so on, the next logical question has to be, how in the world do we solve for all of them at once? How do we find a balance? Well, that brings us to the absolutely crucial concept of systems of linear equations. If you remember one word from this slide, please make it simultaneously. Think about it. A manager can't just make a decision about increasing production over here without it impacting the labor schedule over there. You can't change the labor schedule without thinking about your budget for overtime pay and material flow. All of these decisions are linked. They are inseparable. A system of equations gives us the mathematical framework to respect those connections and find a single solution that works for all of our constraints at the very same time. Now, this is a fundamental rule of algebra, but let's reframe it as a core business principle. For every single unknown factor you need to figure out, like what's the optimal number of product A to make, you need a corresponding known limitation or a constraint to guide your decision. So for example, if you want to figure out X, the quantity of product A, you need an equation that represents, say, your labor constraint. That's one. If you also want to figure out Y, the quantity of product B, you might need a second equation representing your total budget constraint. That's 2. And to solve for Z, maybe your material costs, you might need a third equation that models your supply chain limits. Each constraint gives you one of the equations you need to pinpoint that single best answer. So this is the big takeaway here. Solving a system of equations, it is not some abstract academic exercise. It is the literal mathematical process of doing a manager's job. When you find the values for x, y, and z that make all of your equations true, what you have actually found is the single best production rate, the most efficient way to schedule your employees, and the perfect price point to maximize your company's profit, all while respecting the real-world limits you have to operate within. Now, numbers and equations are incredibly powerful, but let's be honest, they can also be a little abstract. A page full of algebra can be hard to interpret. So let's move on and see how we can turn these systems into a powerful visual tool that allows for at-a-glance understanding and much faster, more intuitive decision-making. We all recognize this. We've seen it 1,000 times in math class. It's a Cartesian plane. It has an x-axis, a y-axis, and we've plotted a simple line. Right now, in this form, it's purely abstract. It's just a picture of an equation. It shows us a relationship, sure, but a relationship between what exactly? But watch what happens when we do something as simple as labeling the axes. Look at that. It's no longer just a graph, it is a management dashboard. The x-axis now represents a critical input, our labor hours. The y-axis represents our key output, how many products we're actually making, and the line itself? The line now visually represents our company's efficiency. The slope of that line tells us how productive we are. We can see, instantly, how many units we get for every single hour of work we invest. And this is really just the beginning. By graphing different kinds of equations, you can visualize some of the most fundamental concepts in all of business. You plot your cost equation and a revenue equation on the same graph, and that point where they intersect, that's your break-even point. That's the magical moment where your company stops losing money and starts making money. You graph all of your production constraints, and the area they create shows you what's called a production possibility frontier. That's basically a map of every possible combination of products you're physically capable of making with the resources you have. It's a visual menu of all your strategic options. All right, let's do it. Let's put all these pieces together. We've talked about equations with multiple variables, we've talked about systems, and we've talked about turning them into visual dashboards. Now let's apply all of it to a concrete resource allocation problem that I promise you every single operations manager on the planet has to deal with. Okay, here's the scenario. Picture yourself as the manager. Your company makes two products, product A and product B. Now you have limited resources. First, you only have so many people working on the factory floor for so many hours a week. That is your labor constraint. Second, your supplier can only get you a certain amount of raw material each week. That is your material constraint. So given these hard realities, the critical question isn't if you can produce, but what is the exact mix of product A and product B that will generate the absolute maximum possible profit? This isn't a hypothetical puzzle. This is the core question of operations management. This is Tuesday morning. And here is the clear, logical framework you would use to find the answer. Step 1 is easy. You define your variables. Let's say X is the number of units of product A and Y is the number of units of product B. Step 2, you translate your business constraints into mathematical equations. So you'll have one equation for labor, something like the labor for A plus the labor for B has to be less than or equal to our total available labor hours, and you'll write another one for materials. Step 3 is where the visualization comes in. You graph these inequalities. The shaded overlapping area where all your conditions are met, that's called the feasible region. Think of it as your strategic playground. Any point inside that region is a possible production plan. Any point outside is impossible. And finally, step 4. You identify the corner points or vertices of that feasible region. It's a mathematical law that your single best, most profitable solution will always be at one of those corners. You test those few points, find the one that gives the highest profit, and there it is. You've just used a mathematical process to make a perfect strategic decision. All right, let's wrap up by making sure all of this really sinks in. It's one thing to understand the mechanics of how to solve these problems, but it's another thing entirely to apply them effectively in the real world. So let's review the core principles. And just as important, let's talk about the common pitfalls that students, and frankly a lot of junior managers, often fall into. This slide really gets to the heart of it. It shows the difference between just doing the math and thinking like a manager. A very common mistake is to oversimplify the problem, to only think about the budget, for example, while completely ignoring the labor constraints. As we've seen, the correct application models all constraints at the same time. Another error I see all the time is treating this like it's just a number crunching exercise to get a final answer. A strategic manager uses the graph to gain insight, to understand why that answer is the best one. And maybe the biggest mistake of all is failing to see how interconnected everything is. A novice thinks, I'll just make more of product A. A strategic manager knows that decision will steal resources from product B, and they use this system of equations to manage that trade-off intelligently. We'll end today with a thought to carry forward with you. Everything we've done today has been about using this incredible tool to find the single best answer for a world of knowns. We knew our labor costs, we knew our material limits, but the real world, as we all know, is full of uncertainty. So I want you to think about this. How could you use this very same framework, not just to find one answer, but to plan for an unknown future? What happens if your labor costs go up by 10%? What if a supplier cuts your raw materials by half? By simply changing the numbers in your equations and resolving, you can model different scenarios. You can stress test your business. You can prepare for a future that hasn't happened yet. And that is the true superpower of business mathematics.